Hello, welcome back. So we will continue our discussion of conservation equations. I figured we would go over what we've done so far a little bit in a blackboard fashion before moving on. Recall we were discussing the momentum equation. So essentially by way of conservation equations, we discussed mass conservation and right now we are discussing momentum conservation. This is what we're doing. So very briefly, when we talk about mass conservation, we're essentially saying mass conservation is essentially so this quantity would be something like the mass current, if you prefer thinking in terms of drawing an analogy with electrostatics, where this would be the rho would be the charge density and then the quantity rho u would be the j. This is the same thing. This is the very same concept. So one thing to keep in mind, of course, is this d over dt, this quantity is in the Eulerian frame. Okay, it's in the frame of the person who's sitting in the lab and watching stuff go by, right? So, and you remember the relation between the Lagrangian derivative, which is the straight d over dt, not the partial, yeah, and this kind of Eulerian derivative is that this is equal to plus this is the, so if for instance you had something so this operator is the same as this operator. So this time derivative would signify the time changes as discerned by a Lagrangian observer, someone who's moving with the parcel of fluid. Okay, and in case mind you, this is not the same as del dot u. No, it's not. What this would be, for instance, in in Cartesian coordinates, would be something like ux d over dx plus uy d over dy plus so on and so forth. That's what this operator is. Okay, so the mass conservation equation, which is written as d rho dt plus divergence of equals 0, that in Lagrangian coordinates, by way of a Lagrangian observer, it would be this. Okay, so these are the same thing. This and this, the same equation, just a matter of the perspective. So this would be the lab perspective and this would be the perspective of an observer who is moving along with the fluid parcel. Okay, and there's an advantage. There are different advantages in considering different perspective. And there's an advantage with looking at this perspective, and that is it's easy to talk about compressibility or lack thereof, compressibility or incompressibility, while looking at this picture. When you talk about, so you can divide this entire thing by rho, and you can write 1 over rho here, and you can this goes away, right, when you divide by rho. And when you're talking about compressibility, you're talking about a situation where this term is important. When you're talking about incompressibility, if this is equal to 0, then it implies an incompressible flow. right? And so, if, in other words, there are not, as far as the, I mean, according to the person who's moving along with the fluid parcel, there are not too many density changes. Yeah. So, in which case the incompressibility condition boils down to, in which case if this first term is almost equal to 0, that means the second term had better be equal to 0, because the sum of these two is equal to 0. So, therefore, the incompressibility condition, the condition for incompressibility the divergence of u does not have a source or a sink. This is the condition for incompressibility, right. So, now you see, this is an advantage of looking, so it's easy to intuitively easy to understand the condition for incompressibility when one looks at the Lagrangian way of writing down the mass conservation equation, right. So, then why bother with the Eulerian way? Well, there's an advantage, and we also remarked that this is generally true for very subsonic flows. Let's simply keep this in mind for now, and because we have not introduced the speed of sound, we have not said what a subsonic flow is, but let's just keep it in mind and we'll revisit it when the time comes, right. And we also remarked that there's something called the Boussinesq approximation, which is often boils down to the same as the incompressible approximation, but not always. Okay. So, now, why even bother about this way of writing things? Why even bother about this way of writing things then? Why even bother about this way of writing the mass conservation equation? The advantage will manifest itself when we start talking about the momentum conservation equation, but this is what's called the conservative form of writing. This is the conservative form. There is something that's conserved. Of the mass continuity equation. Okay, and the conservative form of any quantity is written as the partial derivative, in other words, the derivative as seen by the lab observer as a partial derivative of that quantity. Okay, in this case, the partial derivative of the mass density plus the divergence of the flux of that quantity, and the mass flux is given by rho u. Okay, so this is what's called the conservative form, the mass continuity equation. And by exact analogy, you can write the conservative form of the momentum continuity equation, which is, if there are no forces acting on the parcel of fluid, it would be okay. This is the conservative form because this is a momentum and this is the flux of momentum. This is the advantage of writing down the conservative form of the momentum continuity equation if there are no forces. And even if there are forces, it's possible to bring those forces in right here into the flux of the momentum very easily. And although it's a bit of a formal way of writing it, you see the advantage. You can immediately, well, here's a momentum density to be precise, momentum per unit volume, and here is a flux of the momentum. And mind you, this UU is not an inner product, it's an outer product. And we have seen what an outer product is. Okay. And if there are forces, so really the momentum continuity equation This is nothing but F equals ma for a fluid parcel, not for a point particle, but for a fluid parcel. In this case, what we did here is this is simply ma. This entire thing is just ma, and we assume that there are no forces. Okay. Now, the thing is, there can be two kinds of forces for a fluid. One is a force F can be a body force or a surface force. Okay. A body force is one which acts throughout the body of the fluid. Yeah. So, the body force density, for instance, the force of gravity. This is one also, if the fluid is charged, then and if it's immersed in an electric field, then that's another, but that's not something we're talking about right now. We are talking about neutral fluids. So this is F, I beg your pardon. Maybe I should erase this and write it a little more clearly. Yeah. So, example of a body force would be rho g. Why is it called a body force? Because this is a force that acts throughout the body of the fluid, throughout the volume of the fluid. Okay. Whereas a surface force is one that acts only on the exposed surfaces. Okay. An example of a surface force would be one where you imagine a little, an imaginary cubical surface. Okay. One of the surfaces can be free or not. Okay. So, these are the different surfaces, and let us label the axes. Let us say this is the x axis, this is the y axis, and this is the minus z axis, because x cross y has to be z. Right. So, if you rotate from x to y, a right handed screw would come out in this direction. So, that would be the minus z axis. Right. So, now you see there can be different kinds of forces on say you concentrate just on this top surface. Yeah. What direction is the outward normal of this surface pointing in? It is pointing this way. Yeah. It is pointing in the y direction. Okay. So, there can be a force on this surface right in the y direction. There can also be a force like this, there can also be a force like this. You agree? And so, since there's a force, and since we're talking about surface forces, it makes sense to talk about forces per unit area. In other words, stresses. And this would be what's called a normal stress, okay? And we call this tau y. And we call this erase this is not very nice. This is tau yy, okay. This would be tau zy, and this would be tau x y. Okay. Tau yy would be a normal force. This is what one normally thinks of as pressure. Okay. The force that's acting normal to the surface. What this means is it's the the second y, this y here, this denotes the direction of the outward normal of the face you're talking about. That's why you have a y here and you have a y here also. Whereas the first y here denotes the direction of the force. So, this is a force acting in the y direction on a face whose outward normal is also in the y direction. This is a force which is acting in the x direction on a surface whose outward normal is pointing in the y direction. and so on and so forth. And tau y is a normal stress, and tau xy, tau zy, these are shear stresses. If you think of a surface like this, that would be a normal stress, whereas this and this are shear stresses. Okay, that's what these are. The reason we brought this up is because when you write F equals ma, remember, right, so this is ma, but what is F? F, you can have two kinds of F. You can have a surface force, which is what we just talked about, and you can have a body force, which is this. Yeah. So therefore, you can simply write down the momentum equation in this way, just by analogy with this. A complete version of the momentum equation then would be, just by analogy with the surface forces and everything, would be this, the conservative form of the momentum equation with forces included. Of momentum equation. With forces would be d over dt of the momentum density plus the divergence of the momentum flux would be equal to minus the divergence of the pressure tensor, where this would be representing the body force and this would be representing the surface force. Okay. And what's inside of this P? Yeah, okay. So a couple of things. What really is, let's just, this UU is really a second order tensor, and the UU would be the outer product of two, this kind of outer product is just like that. Like that, A2, B1, A2, B2. So this would be A2, B3, and so on. That's what the outer product is. That's what this quantity is. And the pressure tensor would essentially be this. In particular, we are talking about the divergence of the pressure tensor, right? So the divergence, so the elements of the pressure tensor, the Pij would just be, when I write tau, I really mean P. This is the same as P. You can think of it as tau yy or Pyy. You can think of tau xy or Pxy, so on and so forth. Yeah, and we need to understand what the divergence of a tensor is. The divergence of tensor simply is this, is simply this. The ith component of the divergence of this is simply where Pij is simply this, or this, okay, or this. Same thing. Okay. So now you see, you have a neat way of folding all this in and saying that you go from here, you can actually absorb this guy in here, so that you can write the momentum equation finally as plus divergence of the quantity we already had plus P equals if I want to include the body forces, I can include it, but for the time being, if we neglect the body forces, I can write this as 0, and this really is a conservative form of the momentum equation with surface forces represented by the divergence of the pressure tensor, with surface forces included. Okay. So this is the advantage of writing things in the conservative form. You can simply, this is again, remember, why am I saying this is the conservative form? This, because this is the same form, a partial derivative of the quantity, in this case the momentum density, plus the flux of the momentum, okay, which also includes pressure forces. They are on the same footing. I shouldn't say pressure forces, I should say surface forces of these kinds. Either the normal surface force, normal surface stress, or tangential surface stresses, tangential or shear stresses, same thing. Okay, so this is one way of writing the momentum equation. If all this seems a little, okay, so before proceeding, I should say that in general we assume that there are, the pressure tensor is Pij, which is something like this. Yeah, so it would, you would have a Pxx, you would have a Pyy, you would have a Pzz, and the cross terms here, here, and here. Yeah, so this would be Pxy, Pxz, and so on and so forth. Yeah, now if on the other hand, and remember these cross terms Pxy, these are all associated with, the cross terms are associated with shears, right? This one and this one. If there is no shear, in other words, and remember shear is associated with viscosity. Shear, the whole concept of shear is that you have, the whole concept of shear is that you consider a fluid that's flowing like this, yeah, and if this is the x direction and that's a y direction, and if you have a gradient in the x directed velocity with respect to y, yeah, the x directed velocity is large here, not so large here, not so large here, not so large here. Only here you would think of this as representing the flow of a viscous fluid, wouldn't you? This seems like, the flow of honey. It's a sticky kind of thing, and right at the bottom the honey is barely flowing, whereas right on the surface it's flowing somewhat vigorously. In other words, there is a non-zero, these cross terms are non-zero. Okay, so this represents shear, and if on the other hand you have a relatively less viscous fluid, say water, you would think that this gradient is not as large. Okay, it's almost as if these vectors are almost the same length, and right at the surface the fluid is able to slip rather freely. Okay, in other words, for an inviscid fluid, there's no such thing as a perfectly inviscid fluid. It's all, these terms are all relative. For an inviscid fluid, these cross terms are not important. It's only the diagonal terms that are important. Okay, so for an inviscid fluid, i.e. viscosity or viscous effects are negligible. In this case, the Pij is simply some scalar pressure times a Kronecker delta. Okay, in other words, it's a situation where all of these are simply the same number, P, 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 and the off diagonal terms are all simply 0. Okay, so this means, a situation where the delta is 1 only when I is equal to j, in other words, only along the diagonal, and the off diagonal, when I is not equal to j, as is the case for this element, this element, this element, and so on and so forth, the off diagonal elements, it's simply 0. Okay, so this is a situation which represents an inviscid fluid, and this is why, and this is where I explain why that's so. I urge you to think, this is my way of explaining it, I urge you to think about this a little more. And in this situation, the momentum equation gets a little simpler, and so I write down the momentum equation once again, the full momentum equation. Plus the divergence of this represents a tensor. This is the full momentum equation. You use this and plus the mass continuity equation. You would have to, essentially what you would do is you would expand out this one, and that's where you will need the mass continuity equation here. You use this, both of these, okay, in the situation when this is not only the diagonal elements of the pressure tensor are non-zero and the rest are 0. In that case, you use this and the mass continuity equation, and essentially you will need the mass continuity equation when you expand out this quantity to get the momentum equation for an inviscid fluid. The momentum equation for an inviscid fluid, you can think of where viscosity is not important. You can write that down as rho. Again, all of this is an Eulerian, as okay, is equal to minus, this is just a scalar, okay, plus if you want to include body forces, you can. Okay, and this is called Euler's equation. Okay, Euler's equation, as it's a different thing than the Eulerian frame. Please, keep this in mind. It's an obvious thing, but I thought I would emphasize this. So this is the momentum equation for an inviscid fluid. In general, this is true for any situation. You can include body forces here if you wish, but as such, this includes a situation where viscosity is included. Okay, so as such, we've already introduced what's called the Navier-Stokes equation. This is it, really. We will discuss it separately in a minute, but this is how the Navier-Stokes equation, which includes viscosity, you realize, right? I mean, when is viscosity important? Viscosity is important when the off-diagonal terms in the pressure tensor are important. And the off-diagonal, in this case, we have not made any statement about whether the pressure tensor only has diagonal terms or not. No, we never said that. Okay. Only afterwards we're specializing to this, and we are using the mass continuity equation in that, and getting the Euler's equation as this. I urge you to carry out the steps. Maybe I'll assign it in your problem set. And so this is the Euler's equation. Now, if you recall the difference between the Eulerian derivative and okay, if you recall this definition and you look at this, okay, you can quickly see that it's possible to write down this equation in Lagrangian form also. Okay, as in it's a little easier in this case. You saw the advantage of writing down the momentum equation in the conservative form in an Eulerian frame. In other words, in the frame from the perspective of a lab observer, you could simply write down the conservative form in exact analogy with the mass conservation equation. You can simply write it down. Of course, body forces were not included, surface forces were not included. When you have to include those, you need a few more complications, but that's okay. You could write it down formally, mathematically. It was very easy to write down, but there's a little bit of physical intuition missing there. By way of physical intuition, it's easier to, let's see if momentum, allow me to write this equation for an inviscid fluid, in other words the Euler equation, okay, written for a Lagrangian observer, in other words an observer, in other words an observer who is moving with the fluid parcel. So what would be the momentum, right, for a person who is moving with the fluid parcel? What would be the rate of change of momentum density? It would simply be rho. That's it, isn't it? So this is my MA. Yeah, and what's the force? Well, as for an inviscid fluid, I mean a fluid is going to flow because there's a pressure difference. Okay, so the pressure is higher here and it's lower here. There's a pressure difference. In other words, there's a gradient in the pressure. That's why this fluid is flowing, right? So the F would be, and there could also be body forces, obviously. You could immediately write this down simply from intuitive physical considerations. So this is an advantage of looking at the momentum equation in a Lagrangian framework. And if you wanted to relate this kind of derivative to this equation to this equation, you can see that the relation between the two kinds of derivatives which it immediately follows. The relation between the straight d over dt and the partial d over dt. If you apply that to this equation, this one immediately follows, right? If you simply apply the fact that and you operate this whole thing on u, right, this immediately follows. So there are advantages to both kinds of descriptions. I simply wanted to point this out. So what we have done now is look at the momentum equation for, well, we really started in full generality. We did include viscous effects when we wrote down the momentum equation like this. Okay, viscosity was indeed included because and then so viscous, just to reiterate, viscous effects are important when the off diagonal terms of the pressure tensor are non-zero. Yeah, but then we specialize to a case where viscous effects are negligible. In other words, we specialize to an inviscid flow where only the diagonal terms of the pressure tensor are non-zero, the other terms of the pressure tensor are zero, and we wrote down the Euler equation. It's a bit of a complicated way of arriving at the Euler equation because you had to also in order to arrive at the Euler equation, you also had to use the mass continuity equation. So you arrived at the Euler equation written in the Eulerian frame, written in the frame of an observer who is in the lab frame. Okay, hence these partial d over dt's, right? You can arrive at the Euler equation written in the Lagrangian frame, in other words, in the frame of an observer who is moving with the fluid, either by looking by drawing the analogy between the partial derivatives and the straight derivatives like this. You can go from, you can use that on this equation, yeah, or you can simply write down from physical considerations. I am moving with a parcel of fluid and I am noticing that the momentum density of that parcel of fluid is changing. What's the rate of change of that momentum density? Well, it's this. And why is it changing? Well, MA is this, and why is it changing? It's because of forces acting on it. And what's the kind of force? I'm not interested in viscosity at the moment. I mean, what causes a force to act on a parcel of fluid? Well, it's probably because there's this pressure difference. Pressure is higher here, lower here, so fluid flows. Okay, more precisely, it's a gradient of pressure. Okay, if the pressure difference is larger over a smaller interval, okay, that matters more. So it's really the gradient of the pressure of the pressure essentially, and on top of that, there can also be body forces acting on it. So I can write down the momentum equation for a Lagrangian observer almost intuitively. But if you want to include viscosity, it's not that intuitively simple. It's better to stick to the formal math. And when you include viscosity, this is the momentum equation, this one on the top. And formally, this is really the Navier-Stokes equation. We will discuss this separately. And before moving on to the Navier-Stokes equation, I would want to discuss a few other things that have to do with streamlines and stream functions and things like what we defined in our study of kinematics. So I would like to do a few of those things and point out a few interesting effects before we move on to discussing the Navier-Stokes equation. And we will also say a few words about the energy equation. So for the time being, we will stop here. Thank you.